excited to have you. So just to give you some background on today's class, we're going to be presenting from beginner to advanced, the top 11 best practices from BIM U. This is going to be a compilation of the best, insights that we have been able to gather from all the experts and faculty members that are part of this exciting university. So yeah, let's go ahead and move on to the next slide and go over a few housekeeping items. So everyone will be muted during the presentation. However, you are free to ask us any questions on the chat panel from GoToWebinar. We will have a Q&A session at the end where we will be answering all your questions, and we also have Kelly join us for that part of the session. So let us know if anything comes up during the class. The webinar is being recorded, so everyone who registered for the session will be getting a link to, review the class afterwards. So you will all receive this email about within a week. We will do our best to get that out as soon as possible to you. But yeah, so with that, I would like to, have Thomas introduce himself. So Thomas, take it away.
Sure. So hello, everyone. I'm Thomas Czerniawski. I'm a faculty member at Arizona State University, and I also am the director of the Edifice Lab. Our research is focused on automating parts of Scan-to-BIM, so I thought participating here would be appropriate. I got my PhD at the University of Texas at Austin in civil engineering, construction management, and computer science. And I did my bachelor's and my master's up in Canada at the University of Waterloo. A fun fact about me, since this is the trend in the faculty of Scan-to-BIM University, my fun fact is that I paint and I sculpt in my free time, and I don't really see myself as being too artistically capable, but with the help of technology, I get by.
Awesome. That's great. So before we actually get started with the content for this class, Thomas would like to address the elephant in the room. So let us know what that's all about.
Sure. All right. All right. The elephant in the room. So there are actually two elephants in the room that need to be addressed. The first is that we're about to fly through over 200 presentation slides. Yeah, so get ready for that. And the elephant that you see on screen is an art project that I recently completed. And I actually laser scanned the head because I needed to design a wall mount, and the back of the head wasn't flat. And so designing that wall mount wasn't really straightforward. But with laser scanning, I was able to do it.
Amazing.
I also used the scan to do a kind of construction mock-up just to make sure that the head fit where it was supposed to. All right, so let's dive in. I'll first explain the genesis of this lecture. The Scan-to-BIM webinars have been an absolute gold mine of information. I'm so thankful for the generosity of the Scan-to-BIM University faculty. All the content I'm about to present is knowledge that they have shared. I'm just the aggregator. Every time one of my students comes to me and asks me about scanning or getting trained on Scan-to-BIM so that they can maybe volunteer in my lab, I point them towards the Scan-to-BIM University webinars because they cover everything. But turns out 15 hours of video is a substantial commitment. So I compressed the 15 hours into this 1 hour lecture, and I structured it as a list of best practices. Be excited about reality capture. Understand your options before purchasing hardware. Ask clients what they intend to do with the scan or the model. Be prepared to estimate jobs based on square footage. Make a scan plan. Mitigate the impacts of point cloud noise. Use a combination of registration techniques. Compromise when modeling an imperfect world. Delegate some modeling to automation. Offer a variety of deliverables and prepare for the future. So the first one, be excited about reality capture. Cameras, lasers, drones, dogs, there's no shortage of exciting high-tech toys to play with. The general concept is this. You have a facility, a physical space you want a digital copy of. You take your reality capture device and you move it through the space you want to digitize. As you move it through the space, you capture 2D, 3D images. The next step is to take this information, bring it together in a process called registration, finding out how all these images relate to one another and fit together. If you do registration well, you're rewarded with a cohesive digital representation of the physical space. And these digital representations can be very detailed. And you're not limited to buildings. You can digitize ships. You can go underground and digitize mines. And these digital representations can be used for all sorts of things: cultural preservation, the creation of building information models that can then be used for engineering analyses and construction simulations. Yes, digital technology. Reality capture can improve our awareness of the state of the world by enabling new forms of simulation, automation, and information sharing. Next, understand your options before purchasing hardware. Entering the space can be overwhelming. A lot of options. I'll start by saying you absolutely should not buy hardware if you do not know what you will be using it for. The facilities you digitize, whether it's a mine, a ship, a hotel, all have unique requirements. Each scanner has pros and cons. At a high level, it's a balancing act between cost, time, mobility, range, resolution, and accuracy. And making things even more complicated, how you use the hardware is important. Expensive scanners will not make up for bad process, and a good process can create decent data even with a cheap scanner. I'll run through some of the major categories of hardware to give you a sense of what's available. First, range cameras or depth cameras. These sell for a few hundred to a few thousand. Their range is typically about 10 meters. Their accuracy is a few centimeters. Pro tip, mounting this camera as you scan to a gimbal while scanning improves performance a lot. Next, tripod mounted terrestrial scanners. These will go for 20,000 on the low end to in excess of 100,000 for high-end stuff. I hesitate to say anything about range, resolution, and accuracy because, well, it depends. But in general, they're fairly long range and really accurate. It's not that one scanner is better than another. It's that some scanners were optimized to work well in some situations versus others. And you need to find out which scanner is optimized to work well for your use case. Do you need scanners that are accurate at long range? Do you need a fast scanner? Do you need a scanner that captures really high quality color? Do you need a scanner that maybe isn't confused by shiny specular objects? One strict differentiator is the IMU versus DAC split. These two strategies are used for measuring which way is up. DACs do it better because they're more sensitive than IMUs, but they're more expensive. When is accurate levelness important? If you look at the image on the right, we see a leaning tower in Venice. Evaluating structural integrity of out-of-plumb structures is a case where measuring levelness is really important. Another case is if the environment is vibrating and levelness is being perturbed during scans. Mobile scanners are faster than terrestrial tripod-mounted scanners, but they're less accurate. They achieve better coverage because effectively you're scanning from millions of perspectives along a scan path. If for logistical reasons you're scanning from an unstable platform like a man lift, a mobile scanner would be better here than a tripod scanner because it's not affected by that movement. Cart systems achieve accuracy somewhere in between tripod mounted and handheld. The wheels of the cart provide an added signal to correct for drift errors during slam. But in exchange for the additional accuracy, you lose mobility. It's more difficult to get upstairs, more difficult to get through cluttered areas. Total stations are more accurate than laser scanners, but instead of taking millions of measurements, canvassing the entire field of view, they're just measuring the same point over and over and over again, hundreds of times, just to get a really accurate reading. Hybrid instruments combine traditional total station with laser scanning functionality. If you're a surveyor and you want to do scanning occasionally, hybrid instruments are a thing to consider. You can mount reality capture hardware to drones and robot dogs to maybe automate data collection or to collect data in dangerous environments or from a different perspective. And there are many specialty scanners. I'll only show two examples here. So you can mount scanners to vehicles to capture infrastructure that is expansive. There are scanners for scanning underwater, but there are many other specialty scanners. All right, do not try to save money on scanner accessories. You bought an expensive piece of equipment, get high quality accessories, because if you don't, you're risking the safety of the hardware and the quality of the data. After you collect data with a scanner, you will be processing that data. Do not try to scrape by with minimum computing specs. Eventually, you'll take on a job that makes you run out of RAM, makes you run out of hard drive space, and it'll be a headache. 32 gigs is the consensus for a minimum RAM spec. Anything less than that and your software will crash. Get a massive solid state drive so that you can be, you can store data and access it quickly. But generally, you should get the best specs you can afford to ensure you have a good time with data processing, and so the hardware is actually good for a few years. Reach out to manufacturers and resellers to get personalized information, and pay close attention to the customer service experience. What kind of relationship is developing? Try to get a sense of things like, how likely are they to help you with an emergency loan in case your hardware isn't working and you're on a deadline? And before purchasing, rent and trial a few units and talk to people that have done what you want to do. I'll throw up some good resources of info for further study. Scan to BIM University has a pretty active LinkedIn group. USIBD, that is the US Institute of Building Documentation, I think they're putting together a pretty extensive guide comparing laser scanners, so look out for that. And the last one was Laser Scanning Forum. Yeah, if you want advice on particular pieces of scanning kit, post your questions on there. It's a great community. Ask clients what they intend to do with the scan or the model. The key to success is understanding what your client needs. Like what questions are they trying to answer? And this understanding is developed through communication. Clients will send you a level of detail spec they adopted from who knows where, because they just don't know much about the process, and so they don't know enough to make their own spec. They assume since someone else got LOD 300 that they might as well get that too. Ask them why they need LOD 300. What questions will they be answering using the model? Walk them through the facility, element by element, system by system, and determine where they need detail and where they do not, where they need accuracy and where they do not. You can always be more accurate. You can always have more detail. And so it's important to determine what's sufficient and not to waste resources exceeding that. Through all this, educate the client on what's possible. The laser scanner is not an X-ray. It works by visible line of sight. Help the client understand what will and will not be represented in the data. There's also the 90-degree rule. This is a concept I'll cover more in the modeling section, but essentially it refers to whether the client needs as-built information or normalized information. As-built is needed if you need the model to be as accurate as possible. Normalized information for example, when you need the model to play nice with design tools that maybe expect things to be straight and parallel and 90 degrees to one another. So then you have to normalize. Include as many people in this upfront discussion as possible. One group might need perfectly normalized components while another needs to know if something's out of plumb. Ask who will be using this data and think through the needs of the people downstream. The more people you can bring on as stakeholders, the more people can share the costs of scanning and modeling. Through this communication, you'll understand the needs of the client. Then you can use your expertise to define project specifications. Make sure everything is spelled out in the contract so there are no misunderstandings. Be prepared to estimate jobs based on square footage. So clients will provide a square footage and ask for a quote. It's very common. And this can be frustrating because it's difficult to estimate jobs on square footage alone without understanding the complexity of the space and what needs to be captured. You will get burned giving an estimate too readily on a project and getting stuck doing more scanning than you expected. But you'll get the square footage so much that you'll get the question so much, you might as well embrace it. Using historical data from your own past jobs, you'll be able to provide a somewhat informed answer to these sorts of questions. When studying historical data, there will be a distribution of costs associated with every square footage. Estimating based on square footage will not be pulling from the center of this distribution, but instead from the top, because you want to hedge against uncertainty and risk. You don't want to go underwater on a project. After a while, you'll have a tool that will help you price jobs. You enter a square footage, number of levels, maybe categorize the space, and it outputs a total fee. If this kind of estimate makes you a little uncomfortable, well, it should. Do try to gather more information if you can. Ask the client to take some photos of the space. On larger projects, ship them a 360 camera, have them walk the site, capture photos, ship the camera back. These photos will greatly inform how you approach a project. And if they allow you, do not hesitate to visit the site, whether it's near your office or across the country. It's a small investment to ensure you do not go underwater on a project because you underestimated complexity. And when very little information is provided up front in the form of floor plans or photos of a space, be guarded. Cover your bases in the contract proposal language. Shall not exceed figures are important for change orders. Like, we estimate 150 scans. If we go over, change order may be required. Make a scan plan. Scan plans are important if you want to ensure all required components, facility areas are adequately represented in the scan, and nothing is missed. It's also important to make sure that the plan will help the registration process. Bluebeam's a great tool for doing this kind of planning. Generally, there are two considerations. First, can the scanner see all the things it needs to see, all the things that need to be modeled? Two, is there enough overlap between scans so that the whole puzzle comes together during registration? For your first few jobs, always collect much more data than you think you need. This will save you on the back end with headaches and trying to make the data work. Different colors represent different scan durations. Not all scans will take the same amount of time. 4 things dictate duration: resolution, quality, color, and if there's any unusual setup. So consider what resolution is required to digitize relevant components. And this is a setting in your scanner. If you're trying to capture small conduit that's mounted high up on the ceiling, a higher resolution will be needed. If the facility is really densely packed with things that you need to model, you might want to use a high density just so that you don't accidentally miss something. Quality is how many times the measurement is repeated. It's not repeated as many times as a total station. You see 8x is the max here. But the more repetitions that are averaged, the more accurate the measurement. All right, color. Always defaults to black and white. It's faster to scan, faster to process, and a fraction of the file size. And for a lot of deliverables, colored scans just don't provide very much value. Some facilities and areas are dark anyways, so you're kind of forced to do black and white unless you bring supplemental lighting. So when might color be necessary? If the scan will be used for marketing, if maybe you know that someone inexperienced will be interpreting the point cloud data, if you'll be modeling materials, if the infrastructure you're scanning is color coded in some way, maybe like a chemical facility that's using tagging and colorization to differentiate utilities, color scans will make it easier to tell what is what. All right, the second consideration. Is there enough overlap between scans so that the puzzle can be assembled afterwards? This relates to scan registration. That is, once you've collected all this data, will you be able to figure out how it all comes together into one coherent representation? I talk about this process more later on, but understand that overlap between scans is really important for this. Do not assume that because your scanner can scan things that are 70 meters away, all you need is one scan location at one end of a hallway and then another one at the opposite end of the hallway. You need scans that'll help you tie all of the rooms that come off of the hallway to the hallway. You're going to want to capture a scan in every single doorway, not for the data, but so everything can be pulled together afterwards. On your scan plan, identify critical tie locations, the areas where it's really important to get good overlap, the one door where it's the only access from an entire side of a building to the other entire side of the building, where if you don't collect good scan data at that doorway, nothing works. And highlight these areas and make sure to do a good job scanning in those areas. Scanning above ceiling requires that you pop ceiling tiles, and it's very similar to the doorway concept. These tile openings are critical for tying what's below to what's above. Use a high-low pattern for this. So it's 3 scans stacked. One below the ceiling to capture the room, one at tile level, and then one above the ceiling to capture all the above ceiling stuff. These 3 scans together facilitate registration. Once you've laid out all the scan locations and the scan parameters, you can output a total time estimate. and then use this documentation as the basis for your field notes. One last thing about scan planning. So be thorough when thinking about logistics. Poor coordination may cause you to end up having to stay an extra day, and you'll have to pay for that out of pocket. To avoid this, include all steps and resources that are going to be required while out in the field. So site safety meetings, meetings with the client, site walkthroughs, waiting for access to spaces, areas with restricted access, time slots, special permissions, roof scanning, maybe being accompanied by a security team, areas that are night scanning only, get information for a site contact, know who will be providing access to locked spaces. And if you need things like ladder or a man lift, make sure you know that ahead of time. This kind of thorough planning demonstrates your professionalism to the client and really puts them at ease as you are let loose on their facility. But be flexible. Things change on site constantly, especially if it's an occupied space. You might go to scan something and find out that you can't get access for maybe another hour. The facility doesn't belong to you. You're a visitor. So you got to accommodate for these things, and being personable, the way you choose to engage with the operations staff, it really goes a long way to making sure that your scan job is successful. And staffing large projects. So minimum of 3 people, 2 scanners, so that everything can be rotating. Especially on multi-day jobs, this will prevent burnout. And if you're performing several services like scanning and drone and 360 photos, all of these things can be done in parallel. And use the contract to protect yourself from things that can go wrong, unexpected logistical challenges when out on site. Specify things like mobilization expectations, access expectations, limited traffic expectations. Like, don't be demanding, just list these as assumptions. Mitigate the impacts of point cloud noise. So you've gone out and you've collected this data. So let's talk about the ways that point clouds are less than perfect. So occlusions are shadows in the point cloud data. This is a big part of why it's important to have a scan plan, so that everything that you want represented in the scan is actually in the line of sight of your reality capture hardware. The mixed pixel effect looks like floating pixels kind of splashing off of the edges of objects. Most scanners do a pretty good job of filtering this kind of noise out, and it's only really severe here because I used a low-cost range camera to capture this. The mixed pixel effect, why does it happen? So laser beams are not infinitely small. When they go out into the environment, they'll hit an edge, but part of the laser will continue on to a surface in the background. And then the actual measurement will be some mixture of the 2 distances. There's also measurement error. All measurement instruments, sorry about that. All measurement instruments have some inherent measurement error. This is why if you slice a point cloud, you'll see this. It's a distribution of points rather than a perfect line. That's typically what is associated with the accuracy metric in marketing material for scanners. There's also instability and vibration of the surfaces that the laser scanner is supported by, and this causes inaccuracy. So we see the kind of the waviness on the edge of the pipe in this scan, and that's caused by vibration of the environment. In addition to vibration, the scanner may also be miscalibrated, maybe because it was dropped, mishandled, or is in an environment where the temperature is changing really quickly. On jobs where accuracy is important, it's good to check for calibration issues by taking measurements with other pieces of equipment. So you add in a total station, you add in an electric tape measure, and you just see, are all of my measurements agreeing with one another? If you're having a calibration issue, you got to send your scanner back to the manufacturer to get it serviced. Now let's talk about the noise that you're going to have to clean out of the scans. And this is usually caused by shiny metallic surfaces, mirrors, glass, water, these kinds of things. So say you've got a mirror in a small room that you're laser scanning. The laser paths looks something like this. If we isolate just the scan path that reflects off of the mirror, we see the measurements are bouncing back into the room. But the laser scanner doesn't know that the laser is changing direction here. And so it actually hallucinates the surfaces on the opposite side of the mirror. And so this is reflection noise. And so what do we do about this kind of noise? If the client will be using the point cloud, you should probably spend more time cleaning it so that it's presentable. Certain kinds of reflective and refractive noise can impact registration. That's where we bring all the scans together. And so the noise needs to be clean. For example, when scanning through internal glazing, like we see on the left side here, these measurements are a problem because they're slightly inaccurate due to refraction, but also closely overlapping good data. We see the two-toned point cloud where the good and bad data are overlapping. This will cause problems during registration, so this type of noise needs to be cleaned out, specifically scan data that's captured through internal glazing. As a side note, something that causes a similar problem is thermal expansion and contraction of the facility that you're scanning. So I spoke with a team that was scanning Venice, and they would start their scanning early in the morning and end late in the afternoon. And the bridge that they started on and ended on actually changed shape due to thermal expansion during the day, and this caused problems for registration. So how to perform cleaning? You've identified problematic data. So what next? Unfortunately, this is mostly manual. You can try to filter using things like the intensity value, but then you risk losing data that maybe is on like HVAC or things that don't scan well. But let's consider the noise in this room here, in the windows. So these windows right here. From an external perspective, we see the noise caused by these windows in the bottom part of the figure. So to delete reflections and refractions, draw bounding geometry. There are tools to do this in registration software. You rely on the scanner's perspective, kind of the bubble view, and you trace the boundary of the problematic surface, the frustum of the scan data. And then you just delete it. And we see that from the exterior, the scan is much cleaner now. And you should know that right now, Recap, a popular software, doesn't allow you to clean scans prior to registration, but pretty much every other software allows for this. And if you're seeing a lot of noise above your facility, you're like, there are no windows or mirrors here, what's going on? It's a good indication that you need to clean your lens. Incidental noise is just irrelevant stuff. Clutter or objects that are in the scan, but they don't benefit you or the client. Clean it if it's getting in the way, otherwise try not to waste your time. And don't delete this kind of noise, hide it instead, because you never know if it will be useful downstream. I'll also define transient noise. It's a kind of incidental noise. This is moving clutter, like people moving around, cars moving around, and so on. Environmental noise. happens with steam, dust, snow, rain. Scanners have filters that eliminate this internally, but for the stuff that the filters miss, you'll just have to go in and manually clip and clean it. Use a combination of registration techniques. So you've gone out, you've collected your data. Assuming you've used a tripod mounted scanner, each scan location will give you a 3D image, a scan from that perspective. So let's open all this data up together and see what it looks like. Not good, kind of a mess. Why is that? It's because right now each scan thinks it's the center of the universe. That is the local coordinate system where is the center of the scanner, the origin, and this clearly needs to be fixed. So how do we take all of the scanned data that we've collected and merge it together into a coherent whole? This process is called registration. Registration is probably the most technically complex step in the scan to BIM process. So what software to use? This is the balance between cost and capabilities. Recap is low cost, but few capabilities. Cyclone is high cost, but you can do just about anything you need to in it. In general, the software provided by the hardware manufacturer is the best option, and larger jobs will often require more capable software. Think like 500 to 1,000 is where you might want to switch. There are two methods for registration, cloud to cloud and with targets. The process of registration requires finding correspondences in scan data. If you can find enough points in adjacent scans that you know to correspond, that is, represent the same point in physical space, you can then bring the two scans together. So how do we find these correspondences? Cloud-to-cloud registration tries to detect these correspondences automatically for you, relying on natural geometric features. Think kind of unique surface configurations within the point clouds. For example, the cloud-to-cloud algorithm may look at these two scans, detect the configuration of the major planes, the walls, and draw correspondences that way. Cloud-to-cloud is very powerful, but it's not perfect. It does fail for many reasons. So let's go through these. So dynamic environments, for example, a warehouse loading bay where trucks are coming and going, cloud-to-cloud tries to find these natural correspondences, but they've moved from one scan to the next, and so they can't be relied on. Lots of reflections and refractions. These cause kind of phantom and distorted planes that shouldn't be used for registration. It tries to find those natural correspondences, but half of what it's relying on are just hallucinations. And so this is also not good. Long corridors, round rooms, scanning outdoors. Why are these a problem? Because of insufficient spatial constraints. And so think about scanning in a long corridor. You have good up-down constraints because of the floor and the ceiling. You have good left-right constraints because of the walls on either side, but you don't have good forward-backward constraints. And so the scans kind of slide along that axis. And for round rooms, they have good translational constraints, but insufficient rotational constraints, and so there's ambiguity there. Repetitive geometry. For example, here we have a hotel where each room is the same as the next. How does the cloud-to-cloud know what room the scan was captured in? They can't know. And the same problem with the flight of stairs on the right side here. Each flight of stairs is the same as all others. And here there's repetitive geometry and poor spatial constraints. And so this kind of environment will also be problematic for cloud to cloud. And so in these kinds of challenging environments, you'll need to supplement the cloud to cloud with something, and that's with targets. Remember, registration relies on correspondences, and you can directly place these correspondences in the environment with targets. So Laser Scanning America sells these sphere targets. They're rubber flexi spheres, and they're common because they're durable, but they're also expensive and they're hard to travel with. Paper targets are cheaper, they're easy to travel with, but they have limitations. And that is, paper target should not be relied on when measured from really steep angles. We see the left one here on the wall, measured from a steep angle. And so if we look at the spacing of points at the center of the target here, how far apart are these points? You can't get the center of that target accurately with point spacing like that. So where to place targets? Targets are especially important in critical tie-in areas like doorways, if you remember from scan planning. If a rotational error is introduced at a critical tie-in area, an entire wing of a facility can become misaligned. Think like a lever arm. Where else to add targets? Places where natural features do not offer enough spatial constraints, placing targets in long corridors when scanning outdoors, anywhere there's repeated geometry. One thing to be conscious of when starting out, do not set up targets in a regular pattern. The targets need to create unambiguous correspondence, and regular patterns can be ambiguous. You can register like this or translate over another column or some funky stuff. Be more random about placing targets. Don't be afraid to put them on the floor. Sometimes using targets can be inconvenient though. For example, clean rooms are very controlled environments, and so you want to minimize the amount of stuff you bring into them. High traffic areas make targets insecure, and so that kind of defeats the point of them. Sometimes you just don't have time to set up targets, and you have no choice but to do cloud to cloud in these cases. If that wasn't complicated enough, I'll throw one more thing at you, and that's survey control. You may need to have a licensed surveyor come out and measure some of your targets with a total station to get those points really, really accurate. Hiring surveyors is not expensive. If you need survey, do not hesitate to get control done. Consider the 900-foot building. The image in the bottom left is a top view of this building. Cloud to cloud and target registration will do a pretty good job of merging adjacent scans, but each pair of scans will not be perfectly registered. There will be a slight error, and this error accumulates over long distances. And so the corners here can become 7 inches off. Without survey control, your registration software cannot detect these kinds of global inaccuracies. And so survey control increases the accuracy on larger projects, but it also allows you to register with any existing control networks. And using shared coordinate systems can make working with other teams a lot easier. Checking quality of registration. So thin slices of point clouds can reveal misalignments. Slice horizontally, slice vertically, check columns, windows, doors, piping. Look for these kinds of misalignments. And then once you're finished, get a fresh pair of eyes to QC. All techniques have strengths and weaknesses. The best option is to mix all of them together. Most registration constraints will be cloud to cloud, since generally cloud to cloud is really accurate. But does that mean you should only rely on cloud to cloud? No, because of the challenges we've discussed, but also because targeted registration is a lot easier to troubleshoot when things go wrong. So target errors are just easier to understand. You go through, you pick a control point, you deweight it, disable it, and then you go through one by one, re-optimizing, and eventually you'll find what's gone wrong. On smaller jobs, this isn't as important, but you'll run into these issues on larger projects because everything just amplifies. I'll quickly throw in some more advanced concepts. In-field registration is a first pass registration done in the field. Clustering allows you to break the registration process down into manageable pieces. It gives you a little more control over how registration is done and how errors are distributed. And loop closure. So loop closure refers to the practice of ending a sequence of scans where you began, and then constraining the first scan and the last scan to overlap. And this acts as a kind of a check. And any drift that happened will then be corrected for and distributed through that loop using bundle adjustment. And loops can take any number of trajectories. They don't necessarily have to be horizontal, and they can be large loops and small loops. How are we doing for time? Compromise when modeling an imperfect world. Once you're done registration, you have a point cloud that represents the facility. Depending on the client and their needs, this could be your deliverable. However, oftentimes the client needs you to convert the point cloud into a model. This involves recognizing different building systems and components, fitting them to the point cloud data. Your discussion with the client allows you to specify what needs to be modeled and at what level of detail. I'll quickly mention meshing. Point cloud processing software has the ability to take point cloud data and automatically fit this kind of surface mesh, often in the form of a triangulated mesh. And it's quick and easy, and you can create virtual environments that are easier to interpret by people that are inexperienced with point cloud data. And also it's a great way of modeling complex architectural features, as you'll see in the next section on deliverables. All right, but you want a building information model. So what do? First, you have to bring the point cloud into the modeling software. Here you'll have to answer a few basic procedural questions, like are you using the client's modeling template? Does the client have modeling guidelines and specifications? Do you have a solid data management and version control strategy? So you're all set, ready to go. When modeling, use all view types: plan view, elevation view, 3D view, view ranges, crop regions, things that will help you in interpreting the point cloud data. So if you captured in color, the point cloud will be easier to interpret. And if you captured 360 photos, you can do a side-by-side during that interpretation. So let's model this wall here. And I chose this specifically because the wall isn't perfectly aligned with the principal axes of the building. So first, set your view range so that you have a clean view of the wall. Next, pick the wall type. Sometimes picking the specific kind of component is easy, sometimes it's not so easy. Having specialized trade knowledge on the modeling team is important for this kind of selection, but you shouldn't guess. If you don't know, just place a generic component. And when trying to reconcile the specifications in the contract with the information in the point cloud, do not overstate the level of detail in the model. Delivering true LOD 300, you may need access to information that is actually hidden beneath the surfaces that you scanned. Making assumptions can get you into trouble. And when making these kinds of educated guesses, just make sure you're communicating with the client and saying, in some cases, it's an LOD 200 plus. After selecting a wall type, we trace the point cloud. We'll start at the end, and then we'll notice a deviation at the opposite end because the wall is askew. So we start here, we place the wall perfectly aligned with the corner, and when we drag it over to the opposite side, we see this deviation. And so now we have to answer the question, do we normalize or do we not normalize? So it depends on the model's application. If you're using the model to, say, fabricate components and they need to marry existing conditions, you'll probably want to model as close to the point cloud as possible. Other times it makes sense to normalize because maybe the architect wants to pull dimensions off the wall, and so the wall needs to be parallel and at 90 degrees to everything around it. And so you got to make these judgment calls. You have to compromise. Another consideration, some clients do not like models with fractional dimensions, and so you'll have to model on a grid. So if we want to normalize, how should we normalize? where is the best fit for the wall? Do we just kind of average it so that the middle of the wall perfectly aligns? Sometimes this is a good strategy, but you have to be thoughtful about it. If the model will be used for, say, logistics planning, you may want to err on the side of giving the occupants the perception of having less space than they actually have, so that you don't get any calls complaining afterwards. And if you're instead, say, modeling like a beam that's sagging or deflecting, you might want to align the beam with the supports and the connections rather than just kind of averaging it. A good way to log modeling assumptions and decisions, where you decide to normalize and how severely the scan deviates from the model, is by attaching parameters to the modeled components. Click the boxes depending on what the case is. And then you can visualize the model by filtering out certain cases, viewing others. You should also list modeling assumptions and the compromises that were made in written format so that anyone that needs the information has access to it. Controlling quality of the model. We QC the model using clash detection, deviation analysis software, something like ClearEdge 3D's Verity software, where you can compare the point cloud and the model. And where things between the point cloud and the model, where they don't perfectly align, those things will be identified. You can also bring this stuff into Navisworks, isolate a slice, pull it through the model, and do a visual inspect. Delegate some modeling to automation. So there are three modeling approaches. There's manual tracing, semi-automated, and fully automated. If you've mastered your modeling program, you'll be able to model pretty quickly. On small modeling jobs, there's really no benefit to automation. You just fly through that thing manually. But on larger week-long or maybe month-long modeling projects, you should consider automation. So the amount of automation you can employ depends on two things: the type of building and the disciplines that you're modeling. If you're modeling a castle, your amount of automation will probably be zero. You're going to want to carefully interpret the point cloud data and make sure that someone specialized in this kind of architecture is there to help. If, on the other hand, you're modeling an industrial processing plant or an aircraft hangar, then 80% of the piping and structural steel can be automatically recognized. These simple extruded components can be modeled using semi-automated and fully automated tools. So semi-automated is where you click on some region within the point cloud and the software will fit primitive geometry to those points. Or you can identify a component, like one of the columns here, and define it as a template or a pattern. And then the software searches the point cloud looking for things that match that pattern. And we're limited to semi-automated here because it's impossible to search for every conceivable kind of component. And there's also ambiguity between things like two back-to-back angles and a T. And so it's easier if you just give us software the hint here. But there are fully automated tools. Fully automated searches the entire point cloud for some primitive geometry. Think pipes and walls and floors, extruded geometry in a predefined library. And when using an automated process, you must perform QC because computers make mistakes. There'll be false positives, there'll be things that are missing, but there is software that can help you along in this kind of gap filling process. All right, I think we're about on time. Offer a variety of deliverables. First, what not to do. Do not hand the client a massive hard drive with 57 gigs of something the client has no ability to view or use. It makes the whole industry look bad. Deliver a product that caters to the client's needs and ability. Our deliverable is a tool to help your clients answer questions, make decisions. What questions do they need answered? What deliverables help answer those questions? You have to answer, how is this deliverable going to be consumed and how is it going to facilitate decision making? If your deliverable is a point cloud, make sure your client knows how to use it. If the client needs the fidelity and finer dimensions of the point cloud, you may need to provide some training. There's ways to make the point cloud more user-friendly, like cleaning out noise, making sure it's color, isolating small sections of it, breaking them up into smaller chunks, making sure they have 360 photos to do a side-by-side, taking screenshots, printing out slices. And if you didn't end up modeling the entire facility, you can deliver a hybrid deliverable that has both the point cloud and the model, where the point cloud provides contextual information for any modeled components. And so it's comprehensive, but also cost effective. Site meshes, they can be used for logistics, historical preservation. You can also import small detail meshes into design tools like Revit. Along with the mesh, you can provide a high resolution ortho photo, again, for historical preservation. As built and normalized BIM models. You can also kick out 2D views from these 3D models. These models can be really detailed. They can also be modeled really accurately if they're being used for logistics. Highly detailed historical preservation models. So we see the cornices and the railings here. They were trying to get funding to renovate this space. And so communicating these architectural details was really important. They also kicked out some renders. And there are so many different kinds of analyses and simulation. You can do just about anything you have the ability to with these models. I'll give a few examples. So you can calculate floor flatness, you can do surface deviations, you can do deviations on pressure vessels and holding tanks, structural deflection analysis, installation status and construction progress tracking, installation quality, movement monitoring over time, solar exposure analysis, virtual mock-ups, construction simulations, and the list goes on. But what do you actually give the client? It's almost never the case that the client's going to dive into the nitty-gritty. In most cases, they're going to need some hand-holding. So accompany all the files with a summary report that goes through all the data being handed over. Final deliverable should be a combination of things: graphs, images, animations, spreadsheets, so the client has the option of consuming the information whichever way they prefer. Tell a story with the information in your deliverable. At a minimum, you should have a sit-down meeting with the client and just walk them through the data on their computer, explain to them how they can make the most of the information you've provided. And a final warning: unless you have a licensed surveyor on staff or contract a licensed surveyor, claiming you've done survey can get you into trouble. And two, it's your responsibility to explain to the client the concept of the accuracy food chain. Explain to them what the data can be used for and shouldn't be used for. Like, it's easy to do something for dimensional validation and then repurpose for marketing, but going the other way, not so much. All right, and we're about at time. Do I have like 2 more minutes to go through the last section?
Yeah, why don't you go through it real quick?
Yeah, just 2 more minutes. Sorry about that. So prepare for the future. So during the Automate Everything webinar, they mentioned deep reality in a project funded by the National Science Foundation. I do very similar work in my lab, think generating digital twins with computer vision. Essentially, the research community is trying to provide better tools for automating scan-to-BIM. The tool will allow you to upload some reality capture data, have computer algorithms that automatically identify individual objects and components, understand what the objects are. This process can involve automatically filling in missing data in point clouds. And the output is a complete representation that has semantic metadata, a digital 3D model where all objects of the facility have been automatically recognized. This process is called semantic segmentation and instance segmentation. I'll also say that I've been so impressed with mobile scanning, and I think that this technology is only getting better and better. And who knows, maybe this will dethrone terrestrial scanning, tripod mounted scanning. Yeah. If you're really into high-tech stuff, I'll just point you into light fields. There's this video on YouTube you should watch. If you haven't seen DALL-E 2, Google DALL-E 2. It'll blow your mind, I promise. And yeah, and that's the end of the presentation. I just wanted to thank, again, all the prior faculty in the Scan to BIM University. All of the content that I've gone through, it's not mine, it's their knowledge. I just brought it together. And yeah, if you want to talk about Scan to BIM, collaborate on research, reach out.
Awesome. Thank you so much, Thomas. That was fantastic. I can't believe you got through all of that in an hour and 2 minutes. So well done. Goodness, yeah, we've got some, we can stick around for another 10 minutes to take questions if anybody would like to. Please plug it into the question section. We did have a couple come in already that I tried to answer while Thomas was talking, because I knew we were going to be right up on the time limit here. One of the questions, I gave a short answer, but any examples of software that can do automated modeling from point clouds? And I know you mentioned Edgewise briefly, and the semantic segmentation stuff is another form. It's kind of a first step towards getting into modeling. Is there anything else that pops into your head that you think you should throw out there for people?
So I'll point the question asker to the Automate Everything webinar. I think you guys did a pretty good job of covering all of the commercial tools that are out there. Obviously, ClearEdge, I think, is the industry standard. I think there's another company based in London that does semantic segmentation for meshes. I'm struggling to remember the name of them.
Point Fuse, yeah.
Point Fuse, yeah. And then there's a smaller company. I think their website is like scantobim.xyz or something like that, where they do kind of like a bit basic semi-automated, where you click on part of a point cloud and it fits like a pipe to that section. If I'm not mistaken, Faro has some capability to do that as well.
Yeah, Faro, Trimble, all of them in their kind of in their software that they package their scanners with, they'll do some semi-automated stuff. So fitting of pipes, lots of user input, but certainly way more accurate than manual tracing.
Yeah. But yeah, if that's something you're interested in, I'm a big fan of the Automate Everything webinar. So yeah, just go back and watch that.
And apparently there's something wrong with my audio, but I'll try to do less talking. Well, at least at the moment, the only follow-up questions are commenting about my audio. So, I think you did such a complete and compelling overview that people are still absorbing the information.
It's a lot. This is content I usually go through over the course of 6 hours in my grad class. So yeah, I apologize. I just get excited about the topic and I'm just like, they need all the information.
Well, it certainly was all the information. So I think we will call that a wrap.
Great.
And thank you so much for coming on board, for joining Scan to BIM University. And I will say, at Greg Hale's recommendation, Scan to BIM University is proud to announce that we are giving you a honorary degree in Scan to BIM, official immediately. So
I'm honored.
It's not worth anything, but hey, you got it.
It's worth something to me, Kelly.
Oh, hey, we did get one question. I think it's a good question. Hopefully you can hear me. Why do we model, then work the model to make it more realistic? Is the future a new format for reality representation? From Scott Keller. I don't know that we work to make it more realistic. I think we work to make it less realistic and more abstract.
Yeah,
so
exactly.
that people can understand it.
So one of the topics I go through in my grad class is the concept of abstraction. And when you start working with digital models and simulations, abstraction is really a central concept. And it's essentially, you have, you know, reality on the low end of abstraction. When you capture with reality capture hardware, you're abstracting because you're not able to represent reality in its full level of detail. You're sampling reality. And so with that comes abstraction. And then as you process the point cloud into a building information model that can be used for other things, you're not necessarily increasing the level of detail. You're actually removing information, and you're only distilling the stuff that will inform your decision making. And so you're not really like bringing it closer to reality, or I can't remember exactly what the question was, but you're actually decreasing the level of detail as you're processing the scan, because you're trying to get rid of all the stuff you just don't care about.
Like the vibration of the pipe.
Yes, yes. I mean, I can't off the top of my head imagine any decision where you would want that waviness. Yeah, I don't know. People are creative, so who knows?
Yeah. All right. Well, let's actually wrap there. And yeah, if anybody has any other questions, you can find the professor and I both on the Scan to BIM University group on LinkedIn. Obviously, there's some of his contact details there, and we will get the recording of this webinar out sometime in the next week or two and up on scantobimuniversity.com. And yeah, if you have any other, if you want to dive into some of these topics a little more deeply, please go check out some of the past webinars, because we do go pretty deep on some of them. So, all right.
Yeah, it was fun, Kelly. Thanks for putting this together.
Thanks so much, Thomas. Thanks, Paula. Thanks, Sam. And thanks, everybody, for attending. Adios.
Adios.